Now let's summarize some of the key things that we should have discovered from that previous exercise about a local linear approximation using a tangent line. The accuracy of a local linear approximation depends upon three things. The first one is its distance away from our point of tangency. We can see from these graphs, of course, the further away that we get from point A, our graph is getting further and further away from our tangent line, right, in both of these cases. Okay, one thing that we didn't talk about, but we can definitely see from this graph, is the steepness near A. Would you agree that this exponential function is far steeper around this point, and as we move further and further to the right as x gets bigger, than this, let's say, logarithmic function, right? And so if you compare the differences at each of these values, you can see that the exponential function, its tangent line approximation is not going to be as accurate for as long as the logarithmic function because it's far steeper around this point of tangency. And then the last thing that we just discovered is it's all about the concavity, because if your function is concave up around your function, then your tangent line is going to appear down below and it's going to under approximate the value of your function. Okay, and then if your function is concave down, then your tangent line is going to appear up above it, and it's going to over approximate the value of your function. All depends upon the second derivative. And don't forget, you want to do this around an interval that contains both your point of tangency and the point where you're approximating it, okay? So keep that in mind. So let's take a look at another example here. Example 3, find the linearization of f of x is equal to 2e to the negative x plus 1 at x is equal to negative 1 and use it to approximate f of negative 1.2. Does your answer over or under approximate the actual value of f of negative 1.2? Okay, well, let's see. All right. How are we going to start this whole entire process? Well, we're going to need some paper. Okay, check. And probably a set of crayons and probably a battery charger. Okay, so we want two things. We want a point, and I'm going to get the point first because it's the easier part of this. F of negative 1, plug it into the function. 2e to the negative, negative 1 plus 1, that's to the 0 power. 2e to the 0 power, anything to the 0 power is 1, so this is just equal to 2. We've got the point. Negative 1, comma 2. Yes? Okay. Next, we need our slope. To find our slope, we're going to have to find the derivative. F prime of x is equal to, well, any exponential is its own derivative, so this is 2e to the negative x plus 1 times the derivative of the interior function. So think of this as just this linear function here, which is negative x minus 1. Its derivative would be a negative 1. So times negative, whoops, what is this? What is that? Negative 1. Okay, so I just bring that negative on the outside here as f prime of x is equal to negative 2e to the negative x plus 1. And I need to stick in my point of tangency so I can find the slope there. So f prime of negative 1 is equal to negative 2e to the negative 1 plus 1. Well, we already know that all of this business is just 1, so we get our slope as a negative 2. Okay, so we have a point, we have a slope. Let's write the equation of our tangent line. Y is equal to, y equal to, why don't I do minus 2, so the y value, is equal to negative 2 as a slope, x minus a negative, so plus 1. Okay, so again, since we're finding a linearization of this, I do believe that's exactly what it says, so we're going to need this in, say, y equals form, so I'll have to add that 2 over, and I'll call this L of x is equal to, add the 2 over, minus 2 x plus 1. There we go. There's our linearization of our function. In other words, switch back to your other crayon color. f of x being equal to e 2e to the negative x plus 1 is approximately equal to 2 minus 2 times x plus 1, but just really, really close, close to x is equal to negative 1. All right, we'll take a look at some pictures of graphs and stuff at the end of this, I guess, if you really want to. You can just throw it on Desmos. All right, now what else do we have to do on this one? We have to use our linearization to approximate the value of f of negative 1.2. So let's see. F of negative 1.2 is approximately equal to 2 minus 2 times negative 1.2. Why did I close my parentheses? Plus 1. Okay, let's see. That's going to be negative 0.2, I think. 2 minus 2 times negative 0.2, which is going to make 2 plus 0.4, which is 2.4. Okay, all right, there we go. So we're going to say that f of negative 1.2 is approximately equal to 2.4. Okay, there is one of the major applications of a tangent line to approximate the value of this function. Some weird values, right? So, right, this is what I would be getting. F of negative 1.2 would be equal to exactly 2e to the negative 1.2 plus 1, which is 2e to the, let's see, negative 1.2 plus 1 is 0.2. It's actually negative times the other negative, so 0.2. There we go. So that's basically what we just approximated. 2 times e to the 0.2 power. What's it approximately equal to? About 2.4. All right. Now, unlike that square root graph, this one is maybe a graph we're, I don't know, not quite as familiar with. And being able to tell whether or not our tangent line is up above it or down below it, we're just going to use our second derivative and our concavity in order to be able to make the judgment whether or not our function over or under approximates our function value. So here is our first derivative. Let me pick it up. Yes, this one here, not the one with one stop in it. Let's copy and paste. All right, now let's find the second derivative. So f double prime of x is equal to, it's the same exact thing as what we started with, but then we're going to multiply it times the derivative of this interior function, which is a negative 1 again, which, interestingly, goes back to the original function. Okay. Now remember, I need an argument that is based on some sort of interval. So I need to do an analysis of this derivative, this second derivative, to be able to tell whether it's going to be positive or negative, you know, and around negative 1, right, close to negative 1, and the point of tangency, which is negative 1.2. So this function, its original domain is all real numbers, exponentials. You can plug anything that you want to in for it. And the thing about exponentials is that they have a horizontal asymptote. And so no matter what, this thing is always, even if it's exponential decay like this one, it's always greater than 0. It's always going to be positive for all real numbers. Okay, so since the second derivative is greater than 0, then that means that our function is going to be concave up. So we got a function which is concave up, and then our tangent line then must appear down below it. If the tangent line's down below the graph, then it must be under approximating the value of the function. But you need to point out its concavity. So since our second derivative is greater than 0 for all real x, f of x is always concave up, and the tangent line, let's see, it's under approximates, yes. under approximates the value of the function. Okay, did we exactly answer that question? Well, it says, does your answer over or under approximate the actual value of f of negative 1.2? So since our tangent line is down below here, it's going to be something like this. This was, say, 2.4. So we know that f of negative 1.2 must be greater than 2.4.